So we have Justin Gilmer, who's flown in from SF. He's part of Google Brain there. He was actually the first person to join their residency program, which is highly competitive. He now works with Ian Goodfellow and others on adversarial examples. He holds a PhD in theoretical maths from Rutgers. So with that, Justin, over to you. Thanks.
Hey everyone, I'm Justin Gilmer. This talk is called Motivating the Rules of the Game for Adversarial Example Research. And it's a joint work with my co-authors Ian Goodfellow, Ryan Adams, and George Dahl. Okay, so I'm going to talk today about evasion attacks against machine learning systems. So what is an evasion attack? So say we have a machine learning system that's deployed in the world. It takes inputs X and it makes predictions Y. An evasion attack is when an adversary, say Mallory, comes along and is going to adversarially produce some input to the machine learning system in a way that produces some undesirable behavior, Y. Very common example that should be familiar to everyone is spam detection. Spam detectors are pretty accurate, but adversaries are constantly trying to modify the content of their spam emails in a way that evades detection. And defenders are constantly trying to update their spam classifiers in a way that are able to defend against unforeseen attacks and are trying to be as accurate as possible. Now, another kind of evasion attack that's sort of garnered a lot of research interest recently is the notion of an imperceptible adversarial example. So what is an imperceptible adversarial example? So a few years ago, it was discovered that you can take a state-of-the-art image classifier and basically carefully construct some small adversarial noise in a way that when applied to an image will cause misclassification. And this has been very intriguing, especially because to a human, the starting image and the resulting images appears virtually the same. This change was virtually sort of indistinguishable. And yet to the model, these two images clearly appear very different. And so this is very interesting topic of study, but I think this is often discussed as sort of a major security concern, and that's sort of what I would like to talk about today. And so before I get into that, let me first talk about how they're found. So the way you construct an adversarial example is you take a starting image, say that's correctly classified by your classifier. You define some sort of search region around your image for which you're going to do optimization over. So you're basically going to do gradient descent in image space to change the image in a way that sort of maximizes the model's loss on the resulting image. And so very often you can just start with your image, you can just do a couple steps of gradient descent, and you'll eventually arrive at an image that the model misclassifies. And this works for basically virtually every image model that I'm aware of. It's sort of ubiquitous to basically all machine learning classifiers that you can fool with a fairly small perturbation. And since their discovery, it's been demonstrated you can adversarially fool many systems with imperceptible perturbations. So recently there was a paper that showed that you can fool medical imaging by applying a small imperceptible perturbation to the image to change the model's classification. We've also seen adversarial stop signs demonstrated where researchers showed you could apply small tiny little stickers to a stop sign in a way that will make the machine learning classifier say it's a speed limit sign. There's also been adversarial examples shown for the Google Cloud system where an attacker can say start this image that's correctly classified as skiing and change it in a way that the model says is a dog. And as a result of this intriguing phenomenon, there's been a lot of papers trying to, fix this issue. So there's been over 100 papers written trying to defend against small adversarial perturbations. And a lot of these papers talk about the security concerns that small perturbations invoke. If you read some of these papers, you might see quotes like, this undesirable property has become a major security concern in real-world applications of neural nets, such as self-driving cars and identity recognition. Adversarial examples pose a great security danger for the deployment of commercial machine learning systems. It's not everyone that's sort of saying this. I think a lot of people studying small perturbations sort of view as an intriguing property to research. But in this talk, I really want to take this idea of an adversarial example seriously as a security threat, and really try to understand what are the security implications of imperceptible adversarial examples. Does it matter that a small perturbation works? And in particular, models make lots of errors. So what about these kind of errors? So what is this? This is a test error. So this is Inception v3, state-of-the-art classifier, 3.5% top 5 error rate. It's actually superhuman with respect to test accuracy. That's kind of an interesting number because I think humans will get 5% error rate. That's primarily because humans are not very good at distinguishing different kinds of dogs from each other. But if you dig into the model errors, you will occasionally see an error that a human clearly would not make. And so this is one example of an image that the model is very confident is a burrito. And I think we can all agree that there's no burrito in this picture. Here's another test error that the model is very confident is a taxi cab. And here's an image of a hairspray that the model thinks is a beer bottle, and is 92% confident is a beer bottle. So what about these kind of errors? Are these security concerns? Another paper recently showed that you could fool a model by just randomly rotating an image. So here we have an image that the model says correctly is a revolver, but if you just rotate it sort of randomly, you'll trick the model into saying it's a mousetrap. And same thing for this image of a vulture. If you translate it, rotate it, the model will say it's an orangutan. I sort of did my own little investigation. This is one of the state-of-the-art adversarial defense models, so this model was trained to basically try to resist every small perturbation you could potentially give to the input. And indeed, in fact, this model was robust to small perturbations, but it's not robust to other kinds of changes. So what I did was I just fed in lines at random. I wasn't even doing gradient descent or anything. I was just I just defined a distribution over random lines, and I just applied them to the image at random. And I found it was quite easy to break the model in this way. So here I turned the 0 into a 2, the 7 became a 9, this 4 became a 9, the 0 became an 8, and that 1 became a 4. And so are these security concerns as well? And the thing I'll point out about this attack is I didn't need access to model weights. I just tried 6 lines at random, and I would find an error. So they're quite likely errors, at least in that data distribution. OK, so I think to study security, we should first understand the threat. So let's do some threat modeling. So you can ask the question, what does the attacker know about the system? Attacker might have complete knowledge, might know all the model weights, data, training data, architecture, everything. Attacker might have partial knowledge. Maybe the attacker doesn't know the model weights, but knows the data the model is trained on. Maybe the attacker just has query access. So maybe the attacker can just feed in images at random. And so as you go right to left, you get a stronger attacker. So the more knowledge the attacker has about the system, the more capabilities they'll have, and the stronger they can make their attacks. If you go left to right, I think you get higher likelihood attackers. What I mean by that is not every attacker is going to have access to model weights. Not every attacker is sophisticated and has read a whole bunch of machine learning papers. Attackers might just try dumb things like applying stuff at random. And so I think sort of limited query attacks are sort of more likely to be encountered. But one could also consider some attackers may be sophisticated and might do really strong attacks with complete knowledge. Okay, what is the action space of the attacker? I think that's a really important question. So what control does the attacker Mallory have over the input? And what is she trying to achieve? So in particular, if she's trying to change this picture of a panda, why is she constrained in her modifications? Why is she trying to make an imperceptible perturbation? Could she do this instead? And actually, why is she perturbing anything? If she can change every pixel slightly, she could change every pixel by a lot. Maybe she could just feed in a completely different image. And this makes something we call the test set attack possible, where the attacker could just feed in images from the data distribution at random and eventually stumble upon an error. And if you have a model that makes, say, 0.1% error rate on pandas, that attacker will be successful given enough attempts. So I wanted to distinguish between 2 different potential scenarios. On the left here, there are cases where the attacker sort of chooses the starting point. The attacker has like full control over what input they give to the system. And on the right, there might be scenarios where the attacker sort of handed an image or handed a data point and is trying to perturb it in some way. And sort of based on this taxonomy, we sort of came up with 5 potential security settings that are sort of motivated by real-world systems. And so one setting we call the content-constrained input. So what is this? Content-constrained input is when the attacker, they have full control over the input, and they're trying to produce any input that contains desired content or payload. And so an example of this is image spam. And so here's an actual adversarial example from like a real-world attacker. It's a bit dated of an attack. This is from like 2006 when basically spam detection became pretty good. And a way the attacker started to evade spam detection is they would basically upload spam content as image attachments to emails. And they would get past spam detectors that way. Defenders realized that attackers were doing this, so defenders started to train machine learning classifiers to process all image attachments to detect them for spam. And then when defenders started to do that, attackers basically would start modifying the images they were uploading in a way that sort of evade the spam classifier. And this is sort of what arose out of that cat and mouse game where the attacker basically produced an image that has all this funky stuff in the background, but sort of contains the advertisement or spam content that they had. And so there's this funky text, here at Wall Street Report, we work on what we hear from the street. And so if you imagine the design space of the attacker here, it's really any image that sort of contains the spam content that they're trying to upload. It's very different than they sample a random starting point and then they apply an imperceptible perturbation. They sort of just construct the whole thing from scratch to try to evade detection. Next point in our taxonomy is what we call the non-suspicious input. So the non-suspicious input is when the attacker is basically, they again have full control of the input, but they're trying to choose any input that to a human would appear to be real. And one example of this is we call the voice assistant attack. This is a bit contrived of a setting, but one could imagine a realistic variant of this. So suppose Mallory and Bob are sitting at home, and Bob is a voice assistant. And Mallory wants to mess with Bob, and so Mallory wants to make the voice assistant purchase 100 pizzas. But she wants to do this in a way to not arouse the suspicion of Bob. So, so Mallory could just say, hey, voice assistant, please purchase 100 pizzas. But Bob might hear her. And so she doesn't want to arouse Bob's suspicion. So instead, Mallory produces some adversarial audio that to Bob does not appear suspicious, but to the voice assistant appears to be, or the voice assistant interprets as purchase 100 pizzas. And so if you imagine the search space, design space of Mallory's input, it's still very broad. Like it's any input that to Bob would appear non-suspicious. So Mallory could do like subtle white noise. She could take some music and like adversarially modify it in some way. It's still very different than she's handed some audio file and needs to perturb it in some small way. And people have shown that this is possible. People have shown that you can like adversarially modify some like small white noise in a way that voice assistants or say Siri will interpret as being real audio. Okay. Next on our taxonomy is what we call the unconstrained input. This is sort of just when no constraints all in the adversary. They can just do whatever. And an example of this is the iPhone Face ID unlock. So the iPhone has facial recognition, which people can use to secure their phones. And people have shown that this is vulnerable to at least a pretty sophisticated attack. So what these attackers did is they constructed sort of a full 3D model of the the iPhone owner's face, and if they show if they take a picture of that, or if they show that to the iPhone will unlock. And if you just imagine the design space of this attacker, it's just really anything. And the reason why they need to do a 3D face is because the iPhone uses more than just facial recognition. It uses a 3D depth map and also a heat map to when like classifying. And so the attacker sort of needs the full 3 systems at once. All right, next is the content preserving perturbation. So what is this? So here, Mallory is sort of handed a particular input and wants to perturb it in a way that preserves content. One example of this is what we call the pay-per-view attack. So what's the pay-per-view attack? So say Mallory has a copyrighted Panda documentary that she wants to upload to NetMeTube. But NetMeTube has a copyright detector. And so she can't just upload the video because the copyright detector say like, hey, that's copyrighted content, take that down. And so what does Mallory do? Well, she wants to upload the movie, but she needs to change it in a way that the copyright detector does not realize is copyrighted content. So she might apply some funky symbols and stuff to it. And maybe that's successful. And so if you consider the design space of this attacker here, it's sort of any modification that, any modification you could apply to a video that to a human viewer, they could still watch the video and enjoy it, but it sort of looks different to the machine learning classifier. And so the attacker could apply funky shapes. The attacker could like rotate the video, and maybe the users just rotate their laptop. The attacker could crop and apply weird looking background. And this is actually what attackers do. So here's an example of a real adversarial example of someone uploading copyrighted content to a streaming service. And it's a weird looking picture. It looks like two pictures. This is actually what the movie looks like to the viewer. And so it's this really weird, distorted movie. But people will actually watch this, believe it or not. And this is what attackers actually do. And I think the most common attacks we see in the wild are sort of much more simplistic. This attacker maybe could have done something really sophisticated if they had the model weights, but they didn't have the model weights. And maybe if they tried really hard, they could do one of these imperceptible perturbations, but that would require like training your own classifier. You have to collect a data set of movies, you have to train a classifier, and then you have to do gradient descent and like find some like imperceptible perturbation to the movie that would fool the classifier. That's a lot of work. I think instead the attacker just did the easiest thing, which is you just randomly like mess with the movie in some way, and if you try hard enough, that'll just work. Okay, last in our taxonomy is what they call the indistinguishable perturbation. So this is where the attacker is sort of given a sampled starting image and then needs to perturb it in a way that's imperceptible to a human. It's hard to come up with examples where this is realistic. You could think of some settings where imperceptibly might strengthen the attack. Like attackers might prefer to imperceptibly modify a video to upload to a streaming service, but they're not restricted in that requirement. And I think there's sort of been some confusion in the media and research that that imperceptibility is sort of was intended as a security, realistic threat model. I don't think when people introduced this game, they intended for that to happen. Anyway, moving forward, I think we really need to start thinking like real attackers. So with regard to adversarial stop sign, again, this stop sign was constructed with a team of grad students. It took them a couple weeks. It took them white box access. And it's not always going to be robust to lighting changes, perspective changes. I think if you think from the eyes of the attacker, there are probably far easier ways to achieve this goal that don't involve like actually making a model error. Like maybe the attacker could just go outside and knock over a stop sign. Certainly possible, much easier to pull off. Doesn't require machine learning expertise. And it'd be 100% robust to lighting and perspective changes. Now, that doesn't mean that this isn't a threat. Attackers could do this. But I think there might be simpler ways. I don't think you need gradient descent to fool a stop sign classifier. I mean, remember, this MNIST classifier, all I did was just apply lines at random, and it worked. I think if you did something similar to stop sign, it'd probably work. I haven't actually tried that myself, but I think it'd be interesting for future attack papers, to really try to evaluate what's the easiest way to break a model. And it might not involve gradient descent at all. All right, so what should we do about this problem? How do we defend against these attacks? How do we measure the security of our models? I think in some sense, all of machine learning is trying to fix this problem. We're all trying to reduce test error. We're trying to make our models more accurate. So if we want models that don't classify paper towels as burritos, I mean, you just have to make the model better. Like, you need more data, you need a better model. That's what machine learning is trying to do. And I like test error as a metric because test error is sort of the best estimate of the error rate the model makes in the data distribution. And unfortunately, if test error is bigger than 0, that sort of means the classifier is already vulnerable. And I don't really know how to defend against that. I mean, we're all trying to make our models better. And depending on the system we're trying to secure, the definition of test error may depend on the system and threat model. So for like spam detection, test error is sort of your error rate on, say, the recent distribution of spam email. You might try to anticipate future attacks. Anyway, if attackers are doing this, you could try to do massive data augmentation to basically try to train on every possible transformation an attacker could do. Unfortunately, still, a test error might still be bigger than 0, so you might not be fully secure, but at least you'll make it harder for like the sort of the easiest attacks people try, or people just try random stuff. I also imagine trying to reduce area in a holdout distribution. So models they're fragile in the data distribution. They're also extremely fragile outside the data distribution. So no one really knows right now how to like train a model on, say, regular MNIST and generalize to unseen distributions. That seems like an extremely hard problem, but I think it'd be an interesting one to study. Yeah, I think if we can reduce error rate on holdout distributions, that would at least suggest the model is getting better to unseen distributions. Again, test error is probably still going to be bigger than 0, so we're probably not going to be fully secure, but we might be more secure than we were before. In designing considering real systems, there may be other ways to increase security that don't actually involve like fully securing a model. I mean, the iPhone makes it hard to break by using multiple systems at once. So they use a facial recognizer, they use a 3D depth map, they use heat map. In securing a system, you might have options available that don't, say, involve securing the underlying machine learning classifier. I can imagine other metrics, but again, I think for doing research going forward, I think we need to tie the metric to the system that we're trying to secure. But unfortunately, again, it's hard to beat non-zero, or it's hard to make non-zero test error. Doesn't mean we shouldn't deploy machine learning. I mean, spam detection works really well. And so regarding these 100 papers, that are trying to improve robustness to small perturbations, unfortunately, this imperceptible perturbation is an extremely constrained attack model. And so if you make it hard for an attacker to make a small perturbation, they're probably just going to make a larger perturbation. And one of my complaints about sort of these 100 papers is that the best defenses that we have against small adversarial perturbations increase test error. So in some sense, we're making it harder for attackers to do small modifications, but then we're making it easier for like attackers that are just trying random stuff to fool the model. So it's not clear that we're making progress. I think researchers were surprised at how hard this was to fix. But I think it's related to the fact that test error is still not 0. I think, in my opinion, this is just sort of the nearest test error. And yeah, so defenses just don't generalize to larger perturbations right now. Should we study this? Sure. But I think we should just be clear like why we're studying it. And if we're studying security, I do think we need to like make a realistic threat model. Anyway, so to conclude, machine learning classifiers, they're very brittle. But if we want to study security, I think we really need to understand the threat, do some proper threat modeling. And we need to start thinking like actual attackers. What is the easiest way to break the system? What are all the options available to the attacker? There's a whole lot of great work on spam detection, malware detection that does this. But I think this recent literature is trying to defend against imperceptible adversarial perturbations. It's sort of considering an unrealistic threat model at this point. I think studying high likelihood attacks and defenses would be fruitful. We unfortunately can't defend in the worst case, but maybe we can at least make it harder for attackers who are just trying random stuff to break our models. And again, in thinking about system security, we should think about what systems are critical to secure, what attacks are most likely to encounter. And again, we should tie our security metric to the system being secured. Okay, thanks.
Do you have any questions for Justin? And we'll take a few before lunch.
Sure.
Yep.
Christopher Bonnet, Project Sapiens. Is there any work on this on people that have used transfer learning? Because I imagine most of the computer vision models actually used, most of them probably come from some kind of ResNet or Inception model where you do have access to most of the weights, probably not just the last layers. So actually, lots of people might actually have access to that, lots and lots of information about the net, and so it might actually be easy. Well, getting all that information might not be so hard for some of these models.
Sure.
Is there any work on that? Is there any?
I mean,
I have no idea.
So transfer attacks work very well. So if you have access to training data, you can train your own classifier and do an adversarial attack against your classifier, and it very often transfers to the other classifier. So yeah, and that is a very effective technique.
Arthur ECL. This is a actually great talk and question in general with the attacks, but in a way, these systems haven't been really designed to take into account that they might be attacked, right? So in a way, it's like in an early days of passwords where you could try more than 3 times, and then by brute forcing it, you could just guess the password. But what about actually incorporating some model of the world where, you know, an iPhone could know that it might be, you know, there might be attempts for somebody to trick it, and then it could use sort of situation awareness in this kind of sense to try to, you know, bypass them somehow and not like detect them actually.
Yeah, I mean, I think that's an interesting idea. I just, you know, most machine learning models I know of aren't perfect. And, you know, we can try and make it better, but every sort of defense method I know has non-zero tester. It makes mistakes in the worst case. And I think it's sort of, well, I think to get to zero test error, we need to just make our models more accurate. And it's, we're all trying to do that. It's just, it's hard to get it down to zero, be perfect in every possible input.
But is zero even theoretically possible?
That's a great question. I mean, there's plenty of impossibility theorems about like, you know, hardness results in learning. And so yeah, in certain settings, if you don't have enough data, you just can't get a perfect model. Sure. Yeah. Or anyone. Yeah.
Hi, I'm Robin from Similar AI. So isn't it actually almost a compliment that you're working on interesting problems? And the problems with this kind of attack, much like humans when they're learning from examples, humans have lots of blind spots as well. It's kind of the nature of this kind of learning. And if you do a sufficiently hard problem, then your test error should be more than zero.
Sure. Yeah, I mean, humans have test error in some sense. Models certainly have a lot of errors that humans don't make. And they're just different. Models they're pretty accurate, but they're not, you know, not perfect. Anyway.
Thinking about test error, you said that you might have a 3.5% error from the inception V3, and that some of those would be mistakes a human would never make, like the burrito, whereas a human might have a higher error of 5%, but a lot of that is breeds of dog. What that kind of might imply to me is that test error is the wrong metric, and you want a metric which is more test error weighted by whether it matters or whether a human would make that error.
Absolutely.
Is there research on that kind of thing?
Yeah, I think that's a great question. I'm not aware of any papers that are doing this, but I think that's really important. I mean, this test error isn't really measuring what we want, and you know, for security purposes, we might have different metrics that, you know, some errors might be more costly than others, and you know, I don't have the solution in mind. I think that whatever metric we come up with, we need to tie it to a real system in order to you know, properly you know, sort of measure progress. Yeah. Sure.
Hey, Daniel from Queen Mary University here. So I was wondering about your thoughts on maybe including unsupervised modeling in this problem, because it seems to me like for those attacks that are very obvious and have very unusual inputs, maybe you could have an additional unsupervised model that kind of judges how probable this input is overall. And if it's very unusual, you could kind of reject it completely and try to avoid making any decision at all, instead of always forcing the model to output some decision making. So I wonder what your thoughts on that are, if that has potential.
Yeah. I think that's interesting. You know, so you could imagine trying to distinguish between, I don't know, the natural data distribution or just the distribution that the that you're trying to deploy your model in and try to detect any changes to that distribution. And that's interesting. That is another learning problem where you have like, you have the distribution you care about, and then you have anything else, and you're trying to, I guess, do anomaly detection in that sense. Yeah, I think that may be one effective way to make our models more secure. And it's unclear though. Like I don't know of any papers that are measuring that, say, in a more broader threat model. Right now, there are some papers that are measuring that in the imperceptible attack model, but unfortunately, I think studying that restricted attack model isn't telling us much about less restricted and more realistic attacks.
I'm Jeremy from Bloomberg News. Has there been any work on looking at these models that try to take a sort of more feature level view, particularly for vision, computer vision systems, where you wouldn't be doing sort of pixel by pixel analysis? Because that seems like these imperceptible attacks largely rely on the fact that these systems, their means of perception is very different than, for instance, human perception, where you kind of perceive things at a much higher level. Those systems that have tried to incorporate sort of higher level feature analysis, are they less susceptible to these sorts of attacks?
I mean, so there's plenty of methods that help a little bit for like small imperceptible perturbations, but I'm not aware of any method that helps for like larger perturbations. So there are, I mean, I think that's why the small perturbation problem is so widely studied, because there are a lot of potential approaches that would help for those tiny perturbations, but I'm not aware of anything that generalizes outside that small constrained threat model. And there are some results that suggest that at least on some distributions, this might be impossible to do.
Let me do one last question.
Yeah.
Hi, I'm Dan from UCL. During this presentation, most of the adversarial examples focused on vision. I was interested in if there's been any work looking at when it's applied to language instead.
Yeah, there have been attacks shown for natural language processing systems, and people have shown you can fool Google Translate in some way. There's a lot of interesting work on other systems. Malware detection is widely studied. I was sort of focusing on vision because I think that this imperceptible, intriguing phenomenon was very visually appealing to researchers.